Thanks. Hello, everybody. I believe it is a completely new day, new lecture. Good to see you again. This is our last lecture, and I was conditioned to finish this question on LEZ in order for me to be free from the Q2 lecture of the semester. So here we are. So I managed to get to the point where I can talk about LSD reduction formula. So again, this is the continuation of second kind of lecture where it's a fascinating, deep concept, blah, blah, but like maybe nothing makes sense. Okay, we'll see. So probably you're gonna miss a lot of technical details. So let me just explain what is the formula all about. So first of all, this question is L as Z So before I even derive, I'm just gonna tell you the meaning of it and the version of it first. So diagrammatically, first of all, what are these L, S, D? So L is Lehman. Probably I'm not pronouncing it correctly. I think it's all Russian name. Limanvik. Manvik. So last time we talked about this object, right? This object, great object, which is vacuum to vacuum transition amplitude. But in Heidelberg picture with interacting vacuum with this normalization. So I draw a picture that says if you do the power expansion, power series expansion in J, then you get that diagram that looks like that, but all the endpoint of each particle is attached to the source. Okay. So this is, for instance, seventh order. Oh, yes. Seventh order, well, modulo dot, 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 in this expansion, right? Now, so then this coefficient is Green's function, and this is entering Green's function. That. Now, the formula, the reduction formula, is that says that take this thing. So let's take this thing in the momentum space. So let me just say, mention the formula, and then I will explain. I will derive it, or just end with it. So let's consider the case where I have n p1, p2 to the pn in the initial state, and then I have k1 all the way to the kn. So let's look at the Green function, therefore, minus k1 minus kn, and then p1 pn.
Shouldn't that be n minus n?
N minus
Because there are only n.
Oh, well, I can just correct it like that. And yeah. But you're right. I was right morally. Technically, you are right. Good. So let's look at this. The statement is the following. So first, let's basically ask. This almost looks like a diagram that we need to compute the S matrix, right? Scattering matrix. All you need to do is that somehow you have to make this line eventually asymptotic particle state, right? Asymptotic in state, asymptotic out state. And then chop out the external legs. Remember, when you compute, for instance, diagram like that, right? So the Feynman rule says that, oh, this is equal to minus ig squared because the two vertices, there's internal line propagator. So I'm just gonna put this. But when you do this, you never actually wrote down propagator for the external lines. Yes? And then from this, you know how to compute the estimate. So a cross section, for instance. You square this and the kinematic part we talked about. So yeah, there's a diagram, but somehow I should forget about the external legs. Modulo that external legs eventually turn into asymptotic state. So that's the requirement. So then, starting from this endpoint or n plus endpoint Green's function, then what you have to do, what you want to see is that if you take so this equal to so modulo some subtlety, and then you want to look at the product of m e I squared. Maybe that might be different too. There's a propagator, and then so this is ultimately the formula. So the Green's function, here we go. And then what does it say? Let me read it. Okay, I'm gonna read this equation. So listen carefully. So this is a function of n plus n complex variable, momentum variable. Right? Each of them are four momentum variable. In that high multi-dimensional complex space, I'm gonna go into a specific place where I see m poles and then m poles. Right? And then I'm going to read up the residue of that poles. That residue is the S matrix. Okay, so you compute in principle, off-shell Green's function. Okay, then you zoom in very singular points. How singular? You have poles the same number as number of external legs. And then the residue of that thing is magically the S matrix. Now, mathematically, that sounds super magical. Wow, how come this relation be all ever true? But physically, this is totally sensible thing to say, because starting from generically off-shell endpoint group n plus n Green's function, right? And then you want to send this to on-shell to send it out all the way down to the far path, and then send all this endpoint to the far future to make them asymptotic state. And the only way you can achieve that is put this line like then on-shell, not even like approximately on-shell, right? Because you want to send all the way to time goes to minus infinity. So therefore, you want to demand that each of them satisfy complete on-shell condition. Then you ask, oh, now I'm going to chop it up like that. And this is exactly that process, chop it up. And then you read off what's left over there. That is S matrix. Is the content clear? Yes.
So when you talk about Green function, that's the version of not chopping off the
Yes. So Green's function includes the propagator for external legs as well. So this is before chopping up. So this chopping up process is known as amputation. And the amputation is really cutting off the legs and arms. Right? So it is that. So sometimes people say this diagram amputated the Green's function. meaning you have a Green's function, but not including a propagator for the external lattice. Okay, and that is related to that. Yes.
I understand that the LS reduction formula is related to Green's function and the estimacy.
Yeah.
And in practical, what is too easy to take Green's function or estimacy?
Oh, good. That's a good question. I think it depends. It depends on the theory. If you ask me, like in perturbation theory, for instance, a theory that has some small interaction and then free part, I will just compute this directly. But that also is consistent with the point of Coleman that this part of lecture is beautiful conceptually. Wow, there's a deep relationship. But you can ask, okay, what to use of it? How to use of it, right? I haven't studied a single quantum field theory where I first compute this and then extracted this from that process. I have never done that in practice. But then you can always ask, if it's on the other hand, if I just told you, do what I told you to do, just draw a diagram, never include the external lattice, just compute this and follow my formula for cross section, compute it. You might say, okay, why should I believe it? Right? You will always have that question. Why do I know that such a thing is well defined and can be defined at all? So there's this question of practicality, like how easy things to do versus, or also there's this conceptual part, like whether such a thing can be defined. And I think this is answering to the second part of the question. But that's a great question. Any other question? Good. So I spent enough time to actually explain the meaning of it. Okay, so that is the meaning. That is this reduction formula. Okay, now I'm gonna spend the rest of the time, hopefully, to show this. Okay. Hopefully by 11. 8 a.m. for people watching this book. Not too bad. Okay. So to start, we have to talk about, first of all, note that phi of x in interacting QFT can do many things. So what do I mean by that? So consider, first of all, to illustrate the point, consider 3 QFT. Okay, so you just have a quadratic action. Okay, there, the only non-trivial correlation function that you can possibly ask for is, if you look at this, then you can use creation operator to produce that state, and it is e to the plus it by x, if you remember the field operator with the 1. What it means is that this operator has overlap with the only one particle state with 100% probability, nothing else. Okay? In other words, here, for instance, if you ask your question to yourself, okay, can my field operator, I love this guy, can you please produce a 2-particle state? The answer is no. I will not do it, for instance. So that's what a free QFT does, for instance. On the other hand, if we talk about interacting QFT, now it does many things. So first of all, now let's look at this object. So first of all, I can always write this by translation invariance as this is an operator. That, and then by definition of, so now, I mean, I should have asked actually interactive vacuum, right? So now you all understand that. So this acting on that thing is 0, nothing left. And then this acting on that side will give me either p dot x, and then the statement made in the free QLT was this is exactly 1. Okay. So now this need not be 1. What do I mean by that? In order to illustrate that, so in principle, now if we look at the two particle state coming from the interacting QLT, this may be non-zero. So let me show an example. For instance, so we talked about this. There's a pi. If there's a G interaction, we can split it into N and ball. So if I use this single guy acting on the vacuum, I can turn it to 2 particle state in principle. Right? In principle, it can produce many particle states. It may happen at higher order in the G coupling constant expansion, but nevertheless, it is capable of doing it. So therefore, in interacting QLT, when you see a field operator, first of all, that field operator will not be written in the usual form like A and A dagger expansion. Okay? And it can do a lot of things. So now, to wrap it up, therefore, this is not necessarily 1 in interacting QLT. So in order to make that statement a little bit sharper, let's note that this is a Lorentz invariant function of the momentum. Which means that this is a function of some p squared, right? But if I were to use this one on shell, that means that p squared is equal to m squared, which is constant, which means that this is the constant. And in fact, I'm gonna write this constant as square root of g, the constant. You might say, why? Is that the same z that I wrote before? But which z? I wrote I wrote 2 z, right? One is this thing. And another thing was, if I add the perturbative correction to this, I show you that you can have this. Right? So not this z, but it is that one. Okay, this is renormalization factor. Now it is consistent. So first of all, what is the meaning of that? So field operator in interacting theory can produce a single particle with the same, say, wave function, but with different probability, density probability. Okay, and then it's consistent because so phi square is proportional to z. So single phi will be proportional to square root. You see that? In other words, if you insert the 1 particle state, that thing will include not direct vacuum. That thing. This is the square of that object, and that is proportional to z, right? So each of them better be square root of z. Okay. So wave function renormalization factor knows about probability for that field operator to produce a certain state. Yes.
Well, the interactive state does not only have there's the function.
Say it again.
So there's the other possibility.
Yes, it can have. So for instance, it can have this, it can have that, and many others. Yes.
So I wonder how that always means that.
Oh, but the z only appears. Okay, the z appears in the 2-point function. Oh, your question is, so if I look at not just the 1 particle state here, and then 2 and 3 particles,
Yes.
how do I know that is always that z is equal to that?
Yes.
Is that the question? I think I know that because so diagraphically, starting from the vacuum, I act with the field operator, and then I turn into, say, some single particle state, and then I can eventually come back to vacuum with that. That means that if I plot the diagram, in a sense we talked about in unitarily, I should hit the pole, but the pole part always comes with this z, uniquely z.
So that's always basically just talk about other one, the possible one.
Yeah, so in order to fully address your question, we have to discuss what is known as a spectral representation. Okay, so that will make a sharp connection between these two factors. Okay, and very curious, right? It's an amazing fact about the corner field theory. Another fascinating non-perturbative fact about the corner field theory, known as the Hillman. Is it also semantic? Maybe spectral representation. Okay, it might be the topic of next semester. There was another question.
It's very simple. I think that the vacuum in the yellow box is.
Oh, thanks. Good. Yes. Okay, good. Now, in order to get to the point of LSD reduction formula, so first of all, the first point is that the field in interactive QFT can do a lot of things. Now, why am I talking about this? In order to construct the S matrix, we have to put our finger on the asymptotic state first. We should know how to define asymptotic state, right? In and out state, right? Otherwise, how do I know that this is like random state versus this in and out state? Because S matrix is uniquely overlap between out state with in state. So if I don't know how to talk about in and out state, forget it, right? There's no way to get there. But now this is the thing that I have on my hand. And therefore, I should know, starting from this, which can do a lot of things, which on one hand, very good. On the other hand, is pretty bothering. Because the only thing that I'm interested in that right now is how do I get the asymptotic state out of this thing, which can do a lot of things together. Okay? So the question is, how to construct in and out of asymptotic state from this field in perpetuality. So that's the question. And I just brought up this issue to illustrate that it's not trivial testing. Okay, so in order to define that, Coleman introduces this crazy looking object. I've never seen it before, guys. I knew another version of LSD reduction formula approach, but this is new. So he introduces this object. Which, oh, actually, careful. This is only function of time. I will define soon. Okay. So what is that? So in order to talk about what is F, so F. So in the context of S matrix, we want to talk about a wave vector. Wave vector. Why is that? I want to have a vision that there's a particle here, there's a particle there, they don't overlap each other, right? And then they're so far away each other that they don't interact with them. So there's no overlap at all, even in space and momentum. And then they come together, closer together. At some point, they overlap the imperfect. There must be a notion of separating them apart, which means that it will not do in terms of plane wave. Plane wave is delta function localized in momentum space, which is infinitely broad in the position space. So they will just totally overlap, right? So we need the notion of a wave packet. So wave packet state, which I write it as this F with a profile like F, which you can think of it as particular superposition of the point wave state, and then that particular factor that controls the form of the wave packet, I just call this capital F function. Okay, does that make sense? This is the superposition of the state. And then f of x, if you want, you can think of that as wave function of this thing. Okay, so now given this wave packet, okay, given this wave packet state, I construct out of the field operator this particular operator. So first of all, this is the weird I factor. So this is not Hermitian at all. Okay, even if phi is Hermitian, this is not Hermitian. You can check it. Now, what is this true for? This is good because it gives you a factorized state. How do I check that? So property number one. Oh, I'm going to assume that, first of all, we are going to assume that our field operator has a vanishing vector expectation value. Okay, and then from this you can also show that this object also has a vanishing vector expectation value. You can ask, what does that mean? Okay, there's a physical meaning, there's a physical importance of this thing. First of all, if this doesn't vanish, there will be a phenomenon that is known as spontaneous symmetry breaking, which we haven't talked about at all. Okay, this will be the subject of maybe QF2 or more likely QF2. But anyway, for now, just for technical simplicity, let me just assume this. Okay, which means that there might be a field configuration, but if you just look at the average in the vacuum state, they just average out, nothing happens. That's what this means. Okay, that's a simple final solution. Second property, if you take that thing and then act on the vacuum, eject the vacuum, times t. So if you take this operator, which is a function of t, act on the vacuum, and then just look at with respect to some random state, again, probe state, as we played out already. Then this asymptote, meaning if you take a large Q limit, infinite time limit, either plus or minus, then you will find that it is the same as overlap between some random probe state psi. In particular, this part basically the same as the particle state with that wave packet. So and then let me first write the properties, and then we can talk about expansion proving it or not. So this operator constructed like this form satisfies this property. So let us actually understand the meaning first, and then maybe we can move on first proving the reduction formula. So what does this mean? This may be able to produce a lot of other states too, in principle, at finite time. But this has a nice property that if I take this asymptotic time limit, it only manages to produce a single particle state, but also not only random, not just a random single particle state, but with that prescribed wave packet. So it projects just like the vacuum saturation tree we talked about, right? We start with the free vacuum, and then we evolve with time. We talked about this, and then if we take the time limit, something like that, I show you that this eventually turns into basically interactive vacuum with some overlap, and then the rest of the projected out. This has that property. So if I take this operator and then take this time limit, then basically it turns into a single particle creation operator asymptotically with that wave packet form. But then it is actually genuinely only creation operator with that wave packet shape. It doesn't have a annihilation operator with it. So that's why this is 0. on the other hand. So if I take the time goes to plus minus limit, if I ask this question on the other hand, if this had annihilation in it, then this could have been non-zero. But I'm saying this only has creation, that's why this is 0. So we learned this. I mean, proving this does, manage to do this integration, plugging calculation. So let me, for now, omit that step. Instead, let me use it to prove a more important result. So now, what you want to remember is that this thing prepare you a asymptotic particle state. Only asymptotically, like I told you. If you don't take this limit, this can have overlap with other states. Okay. You can ask for this result. Take the Hermitian conjugate. So take the Hermitian conjugate of that, okay? So let's read about that result, which will be important in what follows. Now, after the dagger, some test state is equal to that, and then the second equation. Right? And if you take the Hermitian conjugate for, say, Hermitian operator phi, then what you do is that you first have a minus side, but second you have f star, right? So here just have f star instead. What does this mean? Now, the Hermitian conjugate of that operator instead behaves like only annihilation operator with wave vector profile F, right? Because if it's acting on vacuum, it kills it, as you see. And then if you act on to the left, also it doesn't kill, but it gives you that, right? In that sense, this is a creation, asymptotic particle creation operator. This is asymptotic particle annihilation operator. Okay, good. Now, in order to talk about scattering, for instance, we want to talk about the two particle state. Okay, so this will be another ingredient we need to talk about asymmetry. So how do we do that? So take a state, for instance, F, which we know how to produce by means of this. Okay. Then take an operator with, say, wave vector described by F wave function, and then take the limit. So now let's first take the limit that t goes to minus infinity. So let's understand the meaning of this equation first. So I have prepared a asymptotic state, probably either from the minus infinity or from the minus infinity or from the plus infinity in time. But that's the same thing, because say if you have a particle going like that, okay, if you look at from the minus infinity time, yes, it's going like that. But if you keep looking at that all the way up to the plus infinity, it's still going like that. Okay, so there's this state. Now you say, oh, okay, I take the particle state. So for instance, this is my F1 state. Then I say, oh, I know what this guy does, right? I know this guy will produce a localized state. The localization is described by this wave vector profile. So if I do that when in the far past, and this will look like what? This will look like F1 and then F2 state together. But now since I'm looking at far past, this will be in state, asymptotic in state. Is that clear? Okay, so this is given. Okay, either produced by here or there, but I know that that's there. And then I'm just looking far past and then producing another guy. I'm adding another guy so that it looks like incoming state. Then exactly same logic. So now let's take the plus infinity limit. So again, there's a one particle state produced. And then I'm acting this guy for the far future. Okay, then that will be asymptotic outlet. Obviously, when I say this, I assume that there is no any overlap in profile between F1 and F2, right? So that's the, of course something I already made. Okay, so this is the preparation. Now let's go. Let's go and tackle the question of LSD reduction. Okay, any question? I think we can make it work. Maybe by greatness. Maybe it's not already greatness because I already passed. Oh no, did I pass? No, not quite. I haven't passed the 3 hours all the way yet, right? But I know you might already have said. Let's finish. Say in 50 minutes. How about that? Okay. You mean this? Good. So so that's I understand probably a little bit confusing point. So let me see if I can explain that. So suppose there is some particle line going like this. Okay, and if you put a interaction vertex like here, for instance, then it turns into an incoming state. On the other hand, if you put interaction pointer like right here, then that turns into outgoing state. What I'm saying is that if you have the free flying single particle state, whether this guy is an in state versus out state depending on where does the interaction happens. Right? With the exact same one particle state, I can make this guy incoming state. I can make this guy outgoing state. So that's the sense. For instance, if I only have this guy, I can't quite say whether this is the incoming state versus outgoing state. I can say the exact same thing with even two particle state. Like suppose I have this. And then if I say like that, you might say, oh yeah, they must be outgoing state like that. Right? But let me draw exact same diagram. But let me just parallel shift like that. Now you might say, oh no, they were actually incoming state. Right? So just with the one particle state, yet you haven't quite specified who they are. And then, but when I specify this one, especially when I say this, I'm assuming the fact that there's no overlap, but they're approaching with this condition. Okay, then that tells me that, yeah, I'm talking about in asymptotic state. And likewise, another question. Okay, so now here is the formula that we want to prove. So suppose I have a wave package which is given by F1, F2. And then I want to look at S matrix, and then another wave package state G1, G2. Okay, and so far we've been talking about S matrix in the context where this is actually momentum eigenstate like the tick. So P1 and P2, right? And then we also said, okay, let's talk about K1, K2, like so, right? So now I start with this wave packet first. And then if you remember, if I take, so there's F, this is that. You see that if I take the momentum eigenstate limit, basically this this had originally in the momentum space, there's a broad distribution like so, but I can turn this into momentum eigenstate or plane wave by stretching like that. And operationally, you see that if I take the limit, that this becomes 2e 2 pi to the cube and delta function, and whatever p prime, this shrink to the wave function, sorry, the plane wave, right? So eventually we're gonna show expression in this language, and then we're gonna take the limit. okay, to turn into the more familiar looking expression with the plan waves as the external state. Okay, so that's how we are gonna approach this question. So okay, let's do that. So the expression that I want to show with some hand waving here and there is the following. So I want to show that this is so I'm just looking at 2 to 2 for now. I have to specify time. Okay. What am I doing? So here's this is what I this is the profile. And then I to the 4, then product of 1 to 4, that's and square acting on Green's function, which in this case 4-point Green's function. So first we want to prove this formula. Okay, so let's first see the similarity of this equation to what we wanted to show. So starting with a Green function, if you will, this is a inverse of a propagator, right? Almost, because this minus this plus occur, one of that thing is sort of propagator. So if this one contained propagator for the external legs, I'm multiplying all of the external legs inverse of that thing. It's chopping out, right? This is amputating part. Okay, and then modulo this p, that's me eccentric. That's the claim. Okay, somewhere here there was a limit was taken to go to the asymptotic state part. Okay, and that will be shown basically now. Okay, so let's see how that works. So in order to show that, basically there's a 4 factors of this thing. So if you look at this expression, there is a I times some integration, and then some profile, and then box plus m squared acting on some operator. Okay, some operator, and then maybe there's some other argument. By operator, I mean it can be function doesn't matter. So this is what? This is a bracket vacuum time order expansion of Heisenberg picture operators, right? So there is a F1, I times F1 with that time acting on that thing, I times F2 with that thing acting on the second argument, and then there are another version with the G star or F star instead of F. So we want to figure out, what is that thing first as a building block. Okay, and this is nothing but 4 times of this thing acting on it. Okay, so basically, operationally, given profile, let me amputate. What does that mean? That's the question here. Okay, let me cut out the external legs. Okay, that's what's happening here. So the answer is A goes to minus infinity, B goes to plus infinity, and then this, and where that object, O A, is defined basically the same way we defined already. Okay. So let's see where this is going. So basically, what we're gonna see is the following. So if I do the first F, that implicating operation, then they will turn whatever the order operator into phi to the F that we studied so far. If I do F1 with the same implication, the field operator here will be turning into phi to the F. Okay? And then from this, one can show that if instead one does, star of X instead of F with implication acting on the O, instead now you get t equals to plus infinity appearing first, and then minus infinity, and then you get this operator function conjugated. So I mean, it's a matter of actually. So in order to actually show that, obviously you have to know where they come from first. Right? So let's see. Since I promised to finish the discussion, let me first use it, but let's actually stare at it and then appreciate the meaning of that. Okay? So this tells you implication with F, and this tells you implication with F star. The difference is that this turns O, whatever the operator appearing here, into O to the F with that time limit. Minus comes first, so past comes first in the future. So if I do the implication with F star, first, because there's a two F and then there's two G stars, I want to know how that works. If you do that, then you turn O into, again, F to the O, also O to the F, but now permutation conjugate. We also talked about permutation conjugate relation somewhere here, right? And then two time limit are flipped. So future comes first and then past. Okay? And again, showing this is a matter of actual computing. Integration by part and so on and so forth. So instead, let me use it to show that expression. Okay? That will save me like 10 minutes. Questions so far before actually now about to do the last part of the practice exercise. Okay, so let's do it. Recall that phi to the F is like a creation operator for the asymptotic state, and then Hermitian conjugate of that is annihilation operator. Okay, so remember that. With that, let's move on. Okay. So this is my starting expression. That thing is my starting expression. So this will be equal to. Okay, I'm gonna use this formula. So there are two. Let me say R1, 2. So it's a terrible. Okay, 1, 2. Okay, and then that thing should come with the R goes to plus infinity first, and then PR goes to minus infinity. So there are two of them, and then there are another two of them, which is 3 and 4. Now minus comes first, and then plus. Okay, so I'm just using all of that, plug in, and then what that gives you is Green's function, but not in terms of original operator, but that in terms of now G1 dagger, G2 dagger, F1, F2. Are you with me? You lost? So this is literally product of the 4 of this. Okay, 2 with F, without star, 2 with a star. So there's a with star, turned into dagger, without a star, turned into just that. And then without a star, F comes first, with star, future comes first. Okay, that's what I did. Good. Now let's study this. So now we have to take all these limits. So let's do it. So this is the last exercise. So let's take the, which one? I don't know. I want to take that limit first. So let's take the F2, time for the F2, which is T4. Let's take the T4 limit first. Okay, so I'm gonna take the T4 limit here. So that one has, in addition to all this, so T4 goes to minus infinity, T4 goes to plus infinity, and I'm honestly writing it. And then time ordering of G1 dagger, by G2 dagger, by F1, which I haven't touched, and then by F2 acting at whatever time. So, oh, I'm sorry. So I shouldn't have done it. Okay. So if I take T goes to minus infinity, so then I'm taking this to the far right, right? Because this is the latest, earliest time. So then, so this space gives me and then now this I'm allowed to write down to the far right of the chain. And then when I acting on the vacuum, I told you that acts as what? Creation operator for the asymptotic state. Okay, so that will create for the state. From the second limit, that means that I have to move this guy to the far left. And that just kills the vacuum, right? Because it only has creation operator, but no annihilation operator. Good. So that's the first limit done. Let's do the second limit. So now I have acting on this side. Step 2. So let's talk about this first. So now I have to send it to far left, sorry, far right. Then we talked about this state, right? So you had a one flying particle, and then you create another guy on top of that. Yes? So that is G1 dagger. Dagger, and that's nothing but F1, F2 now in state. Now, if I take this, and then I have to move this guy all the way to the left, that kills the vector. So that's it. Okay, so 2 more limit to set. Let's talk about the T2. This guy. Okay, that guy. So let's write it out. Now I have to write the for future first, and then past. Then I have in. Okay, let's do it. So future. That means I just move to the left. And then this is like annihilation operator we talked about, not the creation. So it gives me something when act on the vacuum from the right, or to the left. So that gives me G2 asymptotic state with one dagger, F1, F2, in. What about that guy? Minus. So now that guy is a subtle because now this is acting on already existing 2 particles in asymptotic state, right? So I'm gonna write it as phi G1 dagger, and then phi G2 dagger acting on 2 particle asymptotic state, and I'm just gonna call this state to be some state, some that I don't know exactly what it is, but I know it may not be 0. I'm just writing it, right? Okay. Last thing, the T1 limit. Are you with me so far? Okay, good. So let's finish up. So now let me take the T1 limit. So that's right. T1 future first, and then past. And then there are two terms. Okay, so almost ready. So let's work it out one by one. So focus. So future part first. So if I take the future, I acting that way. This is annihilation operator acting on existing future part, right? Particle. That will generate a G1, G2, which is not out state. Okay, and then F1, F2. Dot. Let's look at that. So that gives me minus. When this guy acting on here, I'm gonna create G1 overlap with some state that I don't know exactly what it is. Okay, let's work it out that one. Now I'm gonna take this guy. Yes, I'm gonna take this guy acting on to the far. Sorry. Yes. So this is the start of the particle. So you have to hear well. Listen well. So yes, I'm acting that way, but you know, it's not like I'm acting here and there. I mean, you can interpret it that way. It doesn't matter. This is anyway sandwich between two states, right? The point here is that the interpretation part. Now, when I take this part, but you know, basically acting on here, but understanding the fact that I'm taking the time of that operator to the minus infinity. So there was some guy flying over, and then I'm creating a particle, but as time goes to minus infinity. So this is exactly Hermitian conjugate version of that story. Let's come back here. Look at this. There was some guy, and then I'm gonna take time goes to minus infinity, and then when I do that, this creates the in-state. Where is it? Where is it? This creates in-state. Do the Hermitian conjugation of that thing. So you had some bra state. You had some Hermitian conjugate operator of that thing. And then you can take the time goes to minus infinity. They will give you Hermitian conjugate of that state. Is that clear? So therefore, I'm working on that case. So I'm gonna act on that way, but time goes to minus infinity. So that gives me G1. Oh, this must be G2. Yes. And the in state. And finally, the last one. Okay, so time goes to minus infinity, but the only thing that this can act on is here. But this only has an annihilation operator. So it's gonna wait. No. Yes, annihilation operator. So it's gonna create, but with the plus sign, because two minus and cancels, G1, F1, sub. Good. So we are done here. Basically, these two cancel. And then S operator is defined exactly G1, G2, turning into in, because S is nothing but unitary basis change between out and in. And then this is F1, F2, in. So combine that two, you get S minus 1 sandwiched between these two states. So it's a long story. I think there's a lot to be appreciated by actually looking into the formulas more. But at the end of the day, what we have done is that take the possibly off-shell Green's function, right? With this operation, not just divided by the propagator, but somehow this wave packet business. Because when you do that, did I erase all the formulas? When you amputate with this certain wave packet, it automatically takes a large time limit, right? So because of that, you are forced to take long distance propagation limit. Therefore, you are forced to take on shell limit. Okay. By doing so, you turn things into a asymptotic state, and then you have amputated. So this thing is designed in such a way that you amputate by taking the on shell limit, and then the only thing left over is the S method. So it's a technical proof. For concept, it should be clear. Take the grease function, take the onto limit, amputate. Look at the residue. That is your arithmetic. Okay, but this is the formal way of okay, so great. Let's call it a day. Unless you want another discussion. But any question? Okay, good. So again, thanks for being flexible, coming to the last lecture, and it's been a great fun. And some of you may continue, or you may just burnt out. I'm not gonna look at the question never. That's also fine. But if you find some fun and interesting, you can learn more about other aspects of QFT, actual quantum aspect of QFT, in the second part of the course. And course evaluation, give me all sorts of feedback, okay? Negative feedback is a great one, so that I can improve, okay? So that you can help people who might take the course next semester has a better chance to get the improved lecture. Final exam, we have to check the time, probably next Monday. I said it's a closed book. How long? Are we given 3 hours? Maybe. If it is given 3 hours, it's going to be 3 hours. Again, not all. I mean, I can't promise because you can't say, oh, I don't know 1 + 1. So unless you give me that problem, I can't solve that problem. Then I can help. But I'll provide most of the not so supposed to remember formula. Let's put that way. It is very subjective. Anyway, so that's the goal. Any question? Great. Thanks very much, and see you next week during the exam. Yeah, you'll not forget. Right, yeah.